Hello everyone, I'm your friend Dr. Nachiket Doshi and I'm working as a junior application scientist at Advent Informatics. And today we are going to see a very interesting topic, that is protein-protein docking. So before that, let us understand what are protein-protein interactions. So protein-protein interactions, they are basically specific physical associations between two or more proteins in a way to carry out specific biological functions. Now these interactions, they are usually mediated through different molecular interactions or molecular forces like hydrophobic interactions, van der Waals interactions, electrostatic interactions, and hydrogen bonding and salt bridge interactions. So abnormal protein-protein interactions, they are usually linked with major diseases like cancer, neurodegenerative diseases, autoimmune diseases, viral infections as well. So what is the reason to carry out protein-protein docking? So the major reason is that since proteins are very flexible moieties, they have a lot of inherent flexibility when they are in the solution phase, and that is why it is very difficult to crystallize them out as a complex, and that is where the protein-protein docking can help us, right? So now let us see protein-protein docking in action in MolSoft ICM-Pro. So let us load the two individual proteins first. The first protein is 1-BTP. You can click on enter. So this is the X-ray crystal structure of beta trypsin. Now let us load the other PDB, which is 1-LU0. This is the structure of beta trypsin inhibitor. You can see 1-BTP is just composed of one chain, which is the A chain, whereas 1-LUO is composed of two different chains, A chain and the B chain. Both are equivalent, so you can always delete one of them to save the computational time. So let us go ahead and do that. Additionally, I am also going to delete the glycerol molecule and the zinc atom from this A chain. Just give a right click and click on delete. So this is the structure of beta trypsin inhibitor, and this is the structure of beta trypsin. So firstly, let us convert these XR objects to ICM. To do that, just give a right click, click on convert PDB. In this pop-up, you can select on keep tight waters, optimize hydrogens, optimize histidine, proline, ASN, GLN, cysteine, replace the original, display the result. You can untick the hide missing side chains in order to build the side chains, and you can also assign secondary structure and click on OK. Similarly, let's do the same for the other protein, which is 1-LU0. So now let us load a PDB with the code 1PPE. So as you can see, this is the reported complex available on the PDB database, which is already composed of the two protein chains that we are going to dock. The E chain, that is from the beta trypsin, and the I chain, which is the beta trypsin inhibitor. So in this tutorial, what we are going to do is we are going to take these individual proteins, 1-BTP and 1-LU0, and then we will try to dock them and see if we are getting similar results by checking the ligand RMSD. So to do protein-protein docking, you can go to this docking tab, click on protein-protein, and now there are three different options for you to carry out protein-protein docking. So the older option is to carry it out with the legacy protocol, wherein you can set up your receptor, you can set up your ligand, you can select the epitopes, you can make receptor maps and then run your docking and then carry out refinement of some of the dock poses. But right now what we are going to use is the newer protocol, which is using this option. Now in this pop-up window also, you can see there are two different options. The first one is the global option and the second one is selection of some residues. Now you can run a global search on your receptor as well as your ligand by remaining. Now you can run a global search on your receptor and the ligand by clicking on this global option, which is the default option. However, what we are going to do is we are going to use a method called ODAs, which stands for optimal docking areas. So ODAs will predict different amino acid residues which can be probable to take part in the interface interactions between these two proteins. So to run an ODA, you need to go to Tools, click on 3D Predict and click on Protein Interface by ODAs. So let us first run ODAs for the receptor protein, which is 1 BTP. So I have selected the A chain of 1 BTP, clicked on 3D mesh envelope and create residue table option and click on OK. So after the ODA calculation is done, you can see a new object called G_ODA-A, which has been loaded in the workspace panel. Let us rename this by clicking on, giving a right click and click on rename. Click on OK. Now there are two tables which have been created. So this table is of our interest, wherein it has two different columns. The first column is the residue, the second column is average ODA values. So the more negative the average ODA value, more is the chance of that particular residue participating in the interface interactions. So let us sort these ODA values in the descending order. To do that, you can just go to the top of this column and give a single left click. Now you can see it has selected these residues. Also, let us visualize these residues by toggling on this ODAs. So you can see two colored balls here. The first one is red colored and the other are blue colored. So the ones with red color, they are most probable to take part in these. Similarly, let us go ahead and do ODA calculation for our ligand, that is 1LU0 as well. So here I will select the A chain of 1LU0. I'll use the same options and click on OK. So you can see another object called G_ODA has been loaded here. Now let us rename this as well. Let us also sort these ODA values for my ligand. So now you need to select these top 5 residues in green color notation for your ligand and select the other top 5 residues for your receptor in green color notation. So now you need to select these top 5 residues with the most negative average ODA values for your ligand in an orange color notation, whereas for the receptor, these top 5 residues with the most negative average ODA values will be selected in green colored notation. So to do that, go into the A chain of one LU0, give a right click, click on select by residue numbers, and you simply need to enter these residue numbers that you're seeing here. So 27, 26, 25, 7 and 9, and click on OK. Now to convert these green graphics to orange graphics, you can use this particular option. Now let us do the same sort of selection for the receptor. So firstly, we'll need to shift to the receptor table. Let us visualize the receptor. Again, we'll make the selection in the same way by giving a right click, select by residue numbers, 41, 60, 57, 39 and 192, and click on OK. Now you can see it has gotten selected in green color notation. Now to run docking, protein docking, we'll go into the docking tab. Again, go to protein, click on the run global FFT dock. Herein, the receptor object is 1 BTP. The ligand object is 1 LU0. You can select it from this drop down. Now, there are 4 different sampling modes here: the quick test mode, the coarse mode, the regular mode, and the fine mode. So when you go from a quick test mode to a fine mode, the number of conformations that are explored increase significantly. So a fine mode will explore a lot more conformational space. So let us click on this fine mode. So protein docking in ICM MolSoft is a rigid docking wherein the ligand is given flexibility. So this fine mode will explore all different possible conformational flexibilities of the ligand atom. In our case is the one LU0. You can specify the object for selection if you want. You can just type in 1 PPE here like this. But right now I'm just going to click on none. In the receptor focus residues, you can, as I said, you can run by a global search, but right now we'll just run it with ODAs, and similarly for the ligand as well. You can click on this option which will focus cross contact. So specifically the residues which are interacting in the interface, they will be focused upon. You can specify the contact cutoff. You can increase or decrease the contact cutoff using these options. You can increase the number of parallel cores up till 8. So 8 is the maximum number of parallel cores that can be employed in the protein docking job. So I'll be using these default options and then I'll be clicking on OK. So now after I have clicked on OK, you can see at the right hand bottom corner, the protein docking job has started. So while our protein docking is running, let us see how to calculate ODAs or how are ODAs calculated. So this is an article which was published related to the ODAs and its calculation. So what does ODA do is, it is a tool which identifies different surface patches on the surface of the protein, and it identifies patches with the least docking desolvation energies. So it identifies different amino acid residues which can get a lower energy when they get buried into the surface. So the amino acid residues with the lowest docking desolvation energies are the most negative average ODA values, and they are further selected for interface interactions. So this is the result table that is obtained after your docking job has been completed. So now you can see the first 3 columns are X, Y and Z. These represent translational vectors for one particular docking solution. This is the grid-based energy score for that particular docking solution. The IX and JX are the rotational vectors which are associated with one particular docking solution. These are contact fingerprints, and there is also a cluster tree that has been created here based on the contact fingerprints. Other than that, EL stands for electrostatic energy, VW is van der Waals energy, SF is the surface energy term. You have the total energy, which is a combination of all of these, and then you have cluster. So this represents which particular cluster the conformation belongs to. So now we suggest that you select your best conformations based on the energy. So as much the negative energy, the better is that particular conformation or the binding pose. So to load a particular conformation, you can just give a left click. So you can see a new object called dockpose_1 has been loaded here. So let us toggle this on. So you can see this is the trypsin inhibitor and this is the beta trypsin. So now to run a refinement, what you can do is select this particular row like this, give a right click and click on copy or append one selected row to ICM table and click on new. So you can rename this pose as refinement. So it will create a new table called dockpose_refinement with the first pose like this. Now let us go ahead for refinement of this particular binding pose. To do that, go to docking, protein, and click on run FFT solutions. You can select the poses table, which is dockpose_refinement for me, the effort and the number of processors that can be used for this particular process. You can again select a maximum of 8 processors and then just click on OK. So now refinement has been completed. You can just click on OK. So after the refinement is completed and if you click on OK, this will load a dock_ob_ref. The ref stands for refinement. Now let us see this particular binding pose. So a refinement option will give flexibility to the interface side chains and it will give you an optimum binding pose from the best docking solutions that you have selected. Now let us compare this refined pose with our 1 PPE, which is the reference object. So let us select on the I chain of 1 PPE and change it to orange color notation. Similarly, select the A1 chain of the refined object and it will be selected in green color notation. So these are the two ligands under study. So let us compare them by calculating this RMSD. So to do that, go to Tools, Analysis, RMSD, and I'll simply use these options, the default options, and click on OK. So now you can see the RMSD for this particular docking solution is 3.01, which is well within the acceptable range. The Capri challenge, Capri cutoff, which is a protein states that if the RMSD between the ligand and the reference object for your protein docking is less than 10 angstrom, it is within the acceptable range, and you can see that it is much less than 10 angstrom. You can just click on OK. So that's it for the protein docking tutorial. See you on the other side of the tutorials. Thank you.